area between two curves. Objectives: by the end of this lesson, you should be able to identify the region bounded between two given curves, find points of intersection given two curves, algebraically and with a graphing calculator. When appropriate, set up an integral with respect to y instead of x, because we did x yesterday, that will yield the area between the two curves. Understand when finding the area between two curves will require the setup of two separate integrals. This lesson does have a prereq, and that students should be able to graph familiar, implicitly defined functions and equations that are in terms of variable y. This lesson has a prereq that students be able to find points of intersection on a calculator and the use of the store function STO. Students should have already covered the lesson on area between two curves with respect to x, which is what we did. Okay, so we are interested in finding the area between two curves, but now the notion of top minus bottom, the top function minus the bottom function, top minus bottom isn't there. For example, this is one of the functions that I highlighted, and clearly this function is not above, it's not strictly above the other function, which I'll highlight in a different color for you to see. See? So the yellow function isn't above this function. So if we think about it, if we sweep from left to right, you see how from left to right, for example, say if we want to find the area of this region right here, then notice that the bottom function is just part of this top first function, right? Or say we want to find the area right here. So maybe in this region right here, this is the region where, yes, there is a top function and there is a bottom function. But in the first region that I sketched, this function, let's call this y2 and let's call this y1. Y2 isn't the bottom of this region, so we can't really use top minus bottom because there isn't a bottom here. Whenever that's the case, you can always turn it like this and think of that as top minus bottom because there's always a top function and there's always a bottom function. See how this is the top function and this is the bottom function. If we orient our paper this way, then the top function in this direction is actually the right function in this direction. See? And then this function, which is the bottom function, is the left function. So instead of saying top minus bottom, we go from right minus left. Now when we orient the graph this way, then we're now working in terms of dy. In other words, instead of integrating with respect to x, we're integrating with respect to y. One way to understand that is we now are dividing our area into like strips of rectangle, but they are now this direction, the dy directions, and that's why we have to work in terms of dy. So area between two curves, provided that f is the f function in terms of y is larger than the g function in terms of y for all y between c and d. So this is your c and d. This is going to be your domain. Okay. So to find the area in terms of dy, we take the right function minus the left function. Okay, right function minus left function. If the graph is not provided, we must draw a rough sketch to determine which function is on the right and which function is on the left. If the functions alternate between right and left on the given interval, then multiple integrals may be needed to find the area. If an interval is not provided, we will have to algebraically or graphically determine the point where the two graphs intersect to determine the limit of our integration. So again, whenever you can't do top minus bottom, then we consider right minus left. But in this case, when we do right minus left, we are integrating in terms of the y variable. So we think of this as our domain right here. This is our domain. And then we think of the top function as the right function and the bottom function as the left function. Okay? All right, so here's an example of when we need to do that. Notice that you can't really integrate in terms of top minus bottom because you don't have a different bottom function, you see? So we have to do right minus left, right minus left, right minus left. Okay, so the first thing when we do right minus left is you have to solve for x. So the first thing you have to do is you have to solve for x in both functions. Okay. Now, in the first example, I gave you an example where both functions had x solved, so you don't have to do any work here. The next thing we have to do is we have to identify which function is the left function, which function is the right function. So this function right here is your right function. Okay, that's your right function. And this is the right. And then this other function, which is a vertical line, is going to be your left function. So that's my left function. Now, we set up an integral, and our domain is going to be on the y-axis. So we look and see where they intersect. They do intersect at -2 and 2. So that's going to be our domain, -2 and 2, like that. And then right minus left. Okay, right function minus the left function, dy. So -2 to 2. The right function is 5 minus y squared minus the left function is 1. This is the right function. This is the left function. Solve for x. X are solved for. So that's 1. And then we integrate with respect to dy. All right. So we need to find an antiderivative for this function with respect to y. The antiderivative for y is 5y. The antiderivative for that is y cubed divided by 3. The antiderivative for that is y. And we evaluate this at 2. So this becomes 10 minus 8 over 3 minus 2. And that becomes 10, common denominator is 3, so 30 take away 8 is going to be 22 over 3, and then 22 minus 6, that's going to be, because turning this into over 3, so 22 minus 6 is going to be 16 over 3, so that's f of 2. F of -2, that equals to, when you plug -2 in, you get -10, and that's going to give you a plus here, and that's also going to give you a plus there. So then we have -8, so 24, and that's 16. So that brings us to -16 over 3. Okay. Now, when we find the area, we subtract these two numbers, and when you subtract these two numbers, you get 16 over 3 minus -16 over 3, and that brings it to 32 over 3, and we're done. So the area in this region using the right minus left method is 32 over 3. Okay, that's just one of those rectangles that we're adding up. We're adding up this way. All right, here's another one. Okay, if there is a right function, there's a left function. Strictly, there isn't like an top function minus bottom function. So we have to do it from right minus left. Now, these are the point of intersection, and these are where the right and the left function kind of switch sides. So let's call this region right here, let's call that region our first region. And then let's call this region our second region in here. So we need to find the area between region 1 and region 2. To find the area of region 1 and region 2, then we need to find the area of each region and then add them together. Now, in the first region, we have to do it with respect to dy. So the area, so we need to solve for x in both equations, which we did. They're solved for, and then we set up an area for region 1. So area of region 1, that's equal to the integral from, it seems like they intersect at the y value -1 and 2. So -1 and 2. Now it is going to be the right function, and the right function is this part. This is the right function. Okay, that is the right function right there. So the right function is represented by a quadratic, which is this. That's the right function. So for minus y squared dy, now we look for area of the second region, and the area of the second region is represented. It is from -2 to 1, -2 to 1. The top function is actually this other function right here. This is the top function for the second region. So it is y cubic minus 4y minus the left function. Now in this problem, I did not subtract the left function, so I need to go in and add that in there. The left function is y cubed minus 4y dy. So then you find the area of each one of these, and then you add them together, and that gives you the area of the whole thing. Now to save some time, I'm going to use a calculator to add them together and give you the answer. So I did have to run to get a calculator, so let's do it. So let's go math option 9, and we're integrating from -1 to 2. The function is 4 minus y squared. So when you use a calculator, your x is your y, and then you minus, and then you go x raised to the third minus 4x, and then dy is dx, right? Because these are just variables. And then you integrate, and that gives you 11.25. So the area is 11.25 for the region, for the first region. Now let's do it for the second region and see what it is. So math 9, -2 to 1, x cubed y cubed minus 4y. So your 4x is kind of like your 4y, and then close parentheses for that. Okay, and then here is 4 minus y squared dy. Dx is dy. When you use a calculator, think of dx as dy. Push enter, and that gives you a value of, let me make sure I didn't do anything wrong here, from -2 to 1, -2 to -1, okay? -2 to -1, sorry about that, because area shouldn't be negative, so -2 to -1. So make sure you change that to a -1. That gives you an area of 5.833, and so we add these two together, and that gives us the area of the region we're interested in. So total area is 11.25 plus 5.833, and that equals to 11.833. Okay. All right, here is another one. Set up an integral with respect to x and y separately that will yield the area between the two curves. So we can actually find the area of this region using both methods. Either think of it as top minus bottom, or left right minus left. Now one of those will be easier than the other, but I'll do both so that you can see that they both yield the correct answer. So let's do it using top minus bottom. Okay. In other words, with respect to dx. Okay. With respect to dx. So I have my function here. So my first function here is the function x equals to y squared, which is the function that goes in this direction. And then I have my other function, which is the function a line. This is a line, so I'll make this a little bit darker so that you can see it like that. That's a line function, right? And I'm trying to find the area of that region using top minus bottom. Now, when you move from left to right, notice that this boundary cuts off between top and the bottom function and just the function itself. So if you think about it, in this first region right here, there isn't a bottom function, there isn't a different function. So in this first region, let's call it region 1, and then let's call this region region number 2. Okay, now to find the area in region number 1, then we need to somehow, there's two ways. You can find the area of this part right here and then double it, and that gives you the area of that part. So that's one way. Another way is to figure out what this function is and what this other function is separately, and then integrate the difference, the top function to the bottom function. So let me work with the first region first. So here's what I'm going to do. So here's the area of region 1. Okay. I need to first find the area from 0 to 1 of this region, and to do that, what I'm going to do is, first of all, I know what the function is. It's x equals to y squared. When we do it with respect to x, we need to solve for y. So when you solve for y, you have to take the square root of both sides, and when you take the square root of both sides, you get plus rad x minus rad x. In other words, the function on top, this yellow part right here is the function y equals to rad x, and then this bottom piece right here is actually y equals to negative rad x. So this is a function that's defined implicitly, and therefore it allows us to sketch the graph of that specific function. So the fact that we know which one's top and which one's bottom, then we can find the area of that shaded region by taking the top minus the bottom. So this is the bottom, okay, dx, and that gives the area of region 1. For the sake of time, I will use a calculator to help us accomplish this. And by the way, that becomes 2 rad x dx. So math 9, 0 to 1, and then 2 rad x dx, like that. And the area of that region is 1.333. Okay. Now the area of region 2 is found by taking the integral from 1 to 4, because the cutoff here is 4. So this is region 2 right here. This is region 2, right? 1 to 4 of the top function, which is rad x, minus the bottom function, which is that line, and that line is described by x minus 2. Okay, so we go ahead and type that in math 9, from 1 to 4, radical x minus x minus 2, and that gives us an area of 3.167. Okay, so the whole thing, total area is adding these two numbers together. So we add these two numbers together, and that gives us the total area. Also keep in mind how painful it is to to come up with the area of that region when we do it by top minus bottom. However, when you do it by right minus left, it's a lot nicer. So when we think about it from a right minus left perspective, right minus left, okay, that basically means we're doing it with respect to dy. First, we set up the integral. Right minus left, you have to think of the y values as your bound. So the lowest y value is -1, and the highest y value here is 2. So from -1 to 2. Now your right function is going to be this linear line. This is going to be your right function right here. Okay, that's your right function. So your right function is here. But when you're doing it with respect to y, you need to solve for x. So when you solve for x, you actually get y plus 2 when you solve for x. That's your right function minus, and then your left function. Now this is your left function. Your left function is this guy, okay? The whole thing is your left function. So your left function is actually y squared. So call that y squared, and then integrate that with respect to dy. Now when I type this into the calculator, I should be getting the same number. So let's see. Math 9 from -1 to 2. And by the way, let me show you a quick trick in the event that these two functions are long. So what I can do is I can store the first function under y1. So call it x plus 2, and then store the second function under y2. So y squared, think of it as x squared. Leave that screen. So now you do math 9, and then you get into this function notation. And here's where you type in y1 minus y2. So hit vars, y vars, select y1 minus vars, y vars, select y2, dy, but dx is dy, okay? And then that should give you 4.5. See? 4.5. So very nice. So as you can see, it doesn't matter what method you use, your area will be the same, but in this case, when we do it by right minus left, it saves us time.